Um, okay, so yeah, thank you for inviting me to talk. Um, it's really nice to hear about your society, and I've heard from Liz before about some of the work on the Stanmore Gravels project. So yeah, I'm really happy to come and talk to you today. So today I'm going to talk to you about fluvial landscape reconstruction from the sedimentary record. And here we just have some nice pictures of fluvial formations, and I'll describe those in a little bit more detail in a couple slides' time. So, Liz mentioned there was a Geo-futures theme for this year and said that I might want to share a little bit about my journey to becoming a geologist. So I'll just kind of briefly do that. Um, so Liz did mention my kind of academic history. But yeah, so just to kind of go back to the start, it's actually quite interesting. So I always loved geography in school, but so I went to school down near Portsmouth on the south coast. And my geography teacher realized that I only liked physical geography and that I was just so bored during human geography topics. So she pulled me aside and was like, "Have you ever heard of this thing called geology?" And I was like, "Oh, no, I haven't." So in year 10, we had to do our mandatory 2 weeks work experience placement. And like a lot of my friends in class, like they were kind of emailing like local shops and banks and things to go and do their work experience. And for some mad reason, I emailed the head of department at Portsmouth University asking to do 2 weeks of work experience. And now that I'm an academic, I can't believe that I actually got a reply to my email. But sure enough, the head of department at the time at Portsmouth University emailed me back and he said, "Oh, this is a very strange request. We've not had a request like this before. Um, yeah, why not?" So I got to go to Portsmouth University for 2 weeks. And every day I was left with a different member of staff, whether it was faculty, a professor, or whether it was like a lab technician. And I did an obscene amount of random experiments. I made my own thin sections. I remember being told to use a big drill to cut a thin section to 30 microns. And I was 14 at the time. I was like, I don't know what a micron is. Um, but yeah, so that set me up really nicely. I was like, I know I want to go into geology. So after that, I went to college. I did an A level in geology. I then went on to UCL and I did my integrated bachelor's and master's in earth sciences, then did a year at Nature and then on to do my PhD. And I'm in the US. So yeah, that's a little bit about my journey. I'm very much a field geologist, so I love being out in the field. And during my time, during my PhD, I did a lot of field teaching, which was also great fun. So absolutely love it. You know, I get to see so many amazing places, and I'm out in the US exploring that too. So today I'm going to talk to you primarily about the work that I was doing during my PhD. If you're interested in any particular things, I'm not sure whether Liz mentioned a short course that I co-organized and delivered, but there are 6 sessions, 6 webinars, and they're all recorded and they're stored online, and anyone can access them at any time. So this is going to be kind of skimming the surface, but if you ever want more detail, you can always dive into those 6 webinar sessions. So, just to take it right back to the beginning. So, rivers are the primary conduit of water and sediment across Earth's surface, and they're very sensitive to tectonic and climatic forcing. So, tectonic forcing being things like changes to uplift rates in source regions, earthquakes, landslides, etc. And then kind of climatic forcing, so things like increases in water supply, flooding, etc. Now, in response to these tectonic and climatic forcings, rivers propagate environmental signals throughout their networks. And an environmental signal is just a change in something. So it could be a change in this, mainly a change in sediment production, erosion, transport, and deposition. So a specific example of an environmental signal might be something like a change in the grain size, a change in grain lithology, a change in the amount of sediment, etc., etc. Now, in theory, environmental signals should be preserved in the fluvial stratigraphic record. And these signals, they could be changes, perhaps either up section or along section. And if we can detect these changes and if we can decipher them and figure out what caused them, then this will allow us to gain insights into what ancient landscapes look like and how these landscapes responded to tectonic and climatic forcing. Now, detecting environmental signals requires us to make observations of fluvial stratigraphy, and we can make these observations from outcrop, but we can also make these observations from well log, seismic data, and even orbital imagery. So, like, think of the rover images coming from Mars. So here's just two examples. So perhaps we're looking at a window of observation, which is kind of near the source region of a river system, and then, or maybe we have a window of observation, which is further downstream. So one thing to keep in mind is that when we make observations of fluvial stratigraphy, we're making observations of the depositional realm. So we never preserve this erosional source region. We only preserve this depositional sink region. We might preserve the most proximal parts of it. So perhaps these are kind of alluvial fan deposits. And we might preserve the kind of very distal ends. So the kind of very kind of wetlands, coastal kind of deltaic regions, etc., etc. Now, as a field geologist, I usually make my observations from outcrop. So everything that I'm going to show you today is going to be based on outcrop data. So the next question is well, what does fluvial stratigraphy actually look like? So I just wanted to quickly flag that before we look at some stratigraphy, I wanted to flag just kind of the diverse nature of modern rivers. So modern rivers are highly variable in terms of their geometries, for example. So that could be the width, the depth of these rivers. But they might also vary in their planful morphology. So, for example, do rivers have one single thread? Do they have multiple threads? And then, kind of taking single and multi thread rivers aside, how sinuous are these threads? Rivers also differ in terms of their flow regime. So, for example, some rivers might be perennial and flow all year round, some might be ephemeral and only flow for a fraction of the year. They might also vary in the amount and type of sediment supply. If you kind of get your eye in here, like if you just look at the color of the river here versus the color here, that gives us insights into the amount and type of sediment that's being carried. And they also vary in terms of the land cover that's around them. So we have these like luscious green forests here, whereas down here, this is the desert, and those are actually aeolian dunes. So rivers are super diverse um, on modern Earth. So therefore, we should expect, so with high variability in modern rivers and modern fluvial landscapes, we should also expect highly variable ancient rivers and ancient river landscapes. So I'm just going to show you some examples of these now. So just thinking about the kind of diverse nature of modern rivers, we can kind of get our eye into how different all of these formations are. So hopefully you can appreciate that the scale is different. I've got scale bars in each of them for show. When you're looking in the kind of the finer grained sloping floodplain deposits, there's a lot of variation in color. So here they're nice and red. Here we've got these alternating bands of these grays, orangey reds. Here we've got this kind of like gray into tan colors. And in some places, we don't see these really nice multicolored floodplain deposits. And we also have a lot of variation in terms of the size and amount of these coarse channel deposits. So here we have a kind of ledge. Here we've got kind of ledges peeking through, but here we have an entire cliff. So the main reason I bring this up is because I always think back to geology class in university, and you get shown fluvial stratigraphy and you get shown a 2D log for this is what a meandering river looks like in the rock record, and this is what a braided river looks like in the rock record, and then nothing else. And I kind of always want to like take that page and tear it up because like fluvial systems look so different from one system to the next, and hopefully you can appreciate that from this side. And just because I fear that I've created an illusion that fieldwork is always nice and sunny, here's just another example of the Pennant Sandstone in South Wales. So yeah, we don't always have those nice blue sunny skies. Yes, so now that we can appreciate the kind of the wide variety of fluvial stratigraphy that we get, the next thing is, okay, well, if we look at these and we study them, what can we actually learn? So some of the key questions that I'm particularly interested in when I'm looking at ancient river deposits are things like, well, how was water and sediment distributed across Earth's surface in the past? What was past hydroclimate like? Can we decipher discharge regime or precipitation regime from the rock records? How do ancient rivers respond to changes in climate, land cover, sediment supply, etc.? How did channels and channel belts move across ancient landscapes? And how did landscapes evolve prior to land plant expansion, which can give us insights into how these systems evolved on other planets such as Mars. Now, when we're deciphering ancient landscapes, typically we go out into the field, we make a load of detailed observations, and then we make interpretations from those. So just as a little example here, I've got a picture. So you've seen this image on a previous slide. So this is the PETM succession in the Southern Pyrenees, Spain. So the PETM, it's Paleocene Eocene thermal maximum. It was a global warming event that happened about 55 million years ago. A lot of scientists in many different fields study it because it's a good analog for current warming. And the reason it's a good analog for current warming is firstly because of the temperature rise. So during the PETM, global temperatures rose on average maybe between 5 and 8 degrees Celsius. The cause of the warming was a rapid injection of carbon into the atmosphere. The reason, the exact source or origin of that carbon is debated. It might be methane from the seafloor, or it could be volcanism. And also, the main reason that scientists are interested in it as an analog for modern warming is because it had a geologically rapid onset. So this warming onset and occurred over tens of thousands of years. So we're really good at making qualitative interpretations of fluvial response to change. So we can make inference that climate conditions must have changed during the PETM to lose all of those red floodplain deposits. We're very good at kind of describing what we see. But what I'm particularly interested in is making quantitative interpretations of how these systems responded to change. And the reason I want to do that is if we can get kind of quantitative if we can get constraints on things, this allows us to decipher. So we might observe a change through qualitative observation and interpretation, but through quantitative reconstructions, we might be able to reconstruct, for instance, the magnitude of the change, the duration of the change, the rate of the change. Also, if we can put numbers to these things, this helps us to compare different systems, and it allows us to evaluate or validate our reconstructions against proxy records. So those proxy records might be geochemical proxies of precipitation patterns, etc., etc. So that was kind of the bulk of my PhD work. So I want to make advances in how we quantitatively reconstruct ancient fluvial landscapes. So the main questions that I targeted were, so how do we reconstruct catchment characteristics, such as catchment area, catchment elevations, as this tells us how we might expect systems to respond. So for example, short, steep catchments might have a more drastic response to some kind of perturbation, such as a large influx of rainfall versus large, low sloping catchments. So if you think of a really, really large catchment like the Amazon, storms, et cetera, happening in the source region are likely to be buffered along the course of the river, such that downstream you might not notice the effect of what was happening upstream. The next question I was thinking about was, well, how do we reconstruct river morphologies? How do we establish things like paleoslope, the channel geometries, so the widths, the depths? How do we determine the planned form of these systems? Were they single thread? Were they multi-thread? And this can tell us how channels adjust and the processes by which channels adjust. So if we have a climate perturbation or some kind of tectonic forcing, changes in river morphologies and morphodynamics, they can tell us about the behavior of the river, how sensitive the river is to change, etc. These are also crucial to calculate flow conditions. So, and that's the final question, how do we reconstruct flow conditions? So I'm also interested in things like reconstructing flood hydrographs and sediment supply. This can give us insights into past discharge regime and potentially catchment hydroclimate. So for example, if we can calculate the widths and depths of an ancient river, if we can estimate what flow velocities were, we can get at water discharges. And maybe if we reconstruct an increase in water discharges in a section, this might suggest an increase in precipitation rate, for instance.